So it's now time in the world of wonderful things to introduce our wonderful next guest, Rok Novosel, who is joining us from from Slovenia, from Ljubljana, where he works at he works as a full stack engineer, primarily not on machine learning and deep learning, but he has built a really cool tool as part of the CodeSearch.net challenge that Weights and Biases did with GitHub. It's a really impressive project. It's got some really clear uses, and I'm really excited to hear from him about that. So Rok, go ahead and take it away.
Okay, thank you for the introduction. Hi, my name is Rok, and I would like to present CodeSnippetSearch. It is a web application and a web extension that allows you to search GitHub repositories using natural language queries and code itself, actually. It uses PyTorch to power deep neural networks, which embed natural language queries and code snippets into vectors. So using nearest neighbor search, we can determine which code snippets are most similar to a given query or another code snippet. So why neural code search? Code search, for me at least, is one of the most important tools during coding. I noticed that searching and navigating through code heavily outweighs the actual coding. So when I'm already familiar with the code base, I find that exact search is what I need. For example, regular expressions and case-insensitive search. That is because I'm already familiar with the naming scheme, and I can reasonably predict how to formulate a search query. And basically every IDE and code editor is already equipped with it. But when I'm not familiar with the code base, or even a new folder within an existing large project, for example, it makes searching more difficult because it's more trial and error. A tool like CodeSnippetSearch would allow me to easily explore unfamiliar code, focusing on the semantics without getting bogged down in the syntax. For example, this is especially useful when onboarding a new developer onto a project because it can be a significant boost to their productivity. And here I listed some example queries a new developer could potentially enter. So if you're a new developer and you're working on a product that's using shipping or products or authenticating user or generating QR code, so you don't exactly know how the authentication is implemented. Is it a single method or is it in a class? So basically, instead of trial and error, you just type in authenticate user, and it would return either the function that implements it or the class or some kind of service. So that's where I see the potential behind these methods or behind the CodeSnippetSearch. So outside of a work environment, we encounter unfamiliar code in the form of GitHub repositories, basically every day. So semantic search tools would provide a faster way for users to find answers to their issues directly in the code. Consequently, it could lessen the burden on maintainers to provide these answers. That's why I think it's important for GitHub to explore this option and potentially maybe one day even implement it in their product. So as mentioned, the main data source and inspiration for CodeSnippetSearch is GitHub's CodeSearch.net project. The CodeSearch.net corpus contains approximately 6 million functions from 6 programming languages. These are Go, Python, PHP, Java, Ruby, and JavaScript, where 2 million functions are annotated with a docstring or a comma. So CodeSearch.net, along with Weights and Biases, also hosts a challenge where the goal is to answer 99 queries as best as possible with functions from the corpus. So this challenge is what got me into neural code search in the first place, and also deep learning in general. CodeSearch.net also provides various baseline implementations of neural code search and TensorFlow, and my implementation for CodeSnippetSearch was inspired by their neural bag of words implementation because it was performing the best overall in the published results. So initially, I had written CodeSnippetSearch in Keras, and it was able to search through the CodeSearch.net corpus. But due to difficulties when developing and deploying the models, I decided to switch to PyTorch when I wanted to add support for searching GitHub repositories. Okay, now since I think it's a good time to kind of show you the demo. So this is the demo of totally not cherry-picked examples I wanted to show you. So this is the CodeSnippetSearch application, which is available at codesnippetsearch.net. Currently, I support 31 code repositories because the instance I'm hosting on it is not that large. So that's kind of the limit of what I can get it on. So on the first page, we see the list of supported repositories, their supported languages, and their descriptions. So for the example, I decided to use Django because Django powers the backend of this application. So for the first example, let's try something simple. For example, send mail, which of course returns back a couple of functions that implement send mail. I don't know, email user, email admins, send email message. And as you can see, it returns the link to the GitHub file. So you can click and it returns the highlighted function. Then you also get the match rating, which is kind of a pseudo match rating, which is calculated from the distance between the query and the code itself. And then we get these similar code snippets, which I'll show in a minute. So we can try a slightly more complex query, for example, how to get database table name in Django, right? So here we get table list, which is kind of what we're looking for. So not the exact answers, but I guess any skilled developer could take this function and extract what it needs from it. So to get just the one table name or the table name he's looking for. And to showcase the previously mentioned similar code snippets option, let's say we wanted to look for how to convert time zone to local date time. Okay, and we basically get functions that are able to do the conversion from a specific time zone to a local date time. And if we click on the similar code snippets, so this basically takes this code snippet and it basically searches for similar implementations, similar functions that implement the same functionality. And here we get, as expected, a bunch of time zone converting functions as well. So I mentioned that CodeSnippetSearch also comes in the web extension variety. So if we switch to a GitHub repository, we can open the sidebar by pressing Alt-Shift. The sidebar where you can enter the query the same as before. Let's say since we're on the PyTorch GitHub repository, let's say we wanted to look for one-dimensional convolutions. And as expected, we get back the one-dimensional convolution implemented in PyTorch. That's for fun, just search this in the GitHub search and let's see what we get back. As we see, CodeSnippetSearch is better in every way. So don't use the GitHub search anymore. Of course not. And another feature I would like to show you is the search by code feature, which is basically you select any arbitrary code snippet, you press the right mouse click, and you can select search by code. This basically searches for similar code snippets, and here we get various implementations of the value function from various modules. And here, luckily, we also get, let's say, the leaky value function, which is also implemented, and it's kind of, let's say, a kind of expected result. If you're looking for the value function, you might expect to also see the leaky value function. So this was kind of a quick demo of the function of the web application and the web extension. So I'll just restart the presentation. Okay, so now we can go take a closer look behind the scene. As I mentioned before, CodeSnippetSearch works by using joint embeddings of code and queries to implement a neural search system. The training objective is to map code and corresponding queries onto vectors that are close to each other. With this, I can embed a natural language query and then use nearest neighbor search to return a set of closest code snippets. During training, I use function docstrings or comments as substitutes for natural language queries. So in this image, I have the entire model split up into layers. So first is, of course, the input layer. One input we have for the queries or docstrings, and one input each for languages. So inputs are then forwarded into embedding layers with job multiplied afterward. And basically, the magic happens in the encoding and pooling layer. Here, I take the simplest, but in this case, the most effective way of encoding the tokens, which is using a weighted mean. The weights we use for weighting are learned in a separate layer, in a separate trainable layer. Since we split up the languages at the input, we have to concatenate them back in the same order as they appeared in the queries. And finally, I normalize the rows in the concatenated matrices and multiply them to get cosine similarities. So in the loss functions, the CodeSearchNet implemented a couple of different loss functions, but in general, the loss function can be intuitively explained as maximizing the similarities between the corresponding code and query pairs while minimizing the similarities between non-corresponding pairs. So in this case, the similarity is the cosine similarity. So, and how is the actual searching performed? I take all of the existing code snippets, I encode them, and store them in a nearest neighbors search index. So when I want to look up nearest code snippets using a query, I encode the query, look up the nearest neighbors, and return the most similar ones. I'm using the NOI index, nearest neighbors library, because of the lookup speed, and it's very fast. And since the data set was really large, building the index was time consuming. That forced me to do some open source work and contribute to the NOI index project to implement multi-threaded index builds. So if you're using NOI index, that should be available. And the NOI index was responsible for another little anecdote that happened while working on the CodeSnippetSearch challenge. I've mentioned that I re-implemented their baseline, including the searching part. In my re-implementation, I used the scikit's nearest neighbor search class instead of NOI index because then I wasn't familiar with it. I wasn't expecting a good result on the challenge since I wasn't doing anything special. But it turned out I was at the top of the leaderboard, almost doubling the previous high score. So this kind of puzzled me and the organizers as well. So I did some digging. I swapped out the scikit version, so my version with NOI index, and my score instantly dropped back. It turned out the provided code search evaluation code didn't update the size of the NOI index, and so it returned terrible results. So the lesson is always benchmark the index size if you're using NOI index. Okay, back to CodeSnippetSearch. The training procedure is basically split into two major parts: training the base language models and then training the repository language models with the help of the base language models. First, I trained the base language models using the CodeSearchNet corpus. And the main goal of the base language model is to train the word and code token embeddings that can then be transferred to repository models. Basically, with this, I'm hoping that the base language models learn some general programming language features that can then be fine-tuned by the repository data. With repositories, I was kind of on my own to extract the corpus. So I'm using another GitHub project called TreeSitter to find functions and then tokenize them. So repository models have the exact same structure. I just initialize all embedding layers with base language embeddings. So I just use that as the initial value. And the embeddings are then fine-tuned by training the model with repository code snippet. Okay, and there are, of course, plenty of warnings attached to CodeSnippetSearch. You need a reasonably large, well-documented repository to train the model, and even then it only works on functions. So the first logical step would be to figure out how to work on smaller chunks of code, so a couple of lines of code with a comment above. And from a model perspective, I would like to experiment with tree-based models that could potentially capture the information hidden in the abstract syntax tree. As you've seen in the model image, we're now kind of just ignoring the order, because that seems to work the best when encoding the code on queries. So, but potentially for that, we would need to gather a lot more samples, because even using RNNs or 1D convolutions on these sequences of tokens, they don't work as good as a simple bag of words model. So potentially we would have to gather a lot more samples. So that would be all from me. I hope you like the project. I hope it's potentially useful, and thank you for listening.
Great. Yeah, thanks for sharing, Rok. I've got a lot of questions, and I encourage folks in the audience to submit their own questions as well, but I'll kick us off here. One is, so based off of your experience with the tool, or maybe the way that you tokenize things, how robust is this to typos? You know, like, so if I typed, convolutions, as you did a couple times instead of convolutions, is that going to throw it off, or is it robust to that?
I guess the answer is kind of, because we're kind of using, for tokens, we're using half of it as just a regular vocabulary, and half of it with the byte pair encoding. So we're using kind of the subset of the tokens. So I guess if you misspelled the last part of the word, so the CO and V, I guess it could capture that and still find the appropriate function. So it's kind of robust, but I guess the answer is kind of. As I've said, these were kind of cherry-picked examples. So if you provide a weird input, it's going to provide a weird output for now. But then I'm trying to work on on minimizing the amount of times that happens. But yeah.
I mean, I would imagine a byte pair encoding. So this is for folks who aren't as familiar with natural language. Byte pair encoding tries to find good ways to break words down into subwords and use those and embed those. So it's what's used in the general purpose the generative pre-trained transformer models, the GPT models at OpenAI. That's what they use for their natural language processing stuff. So you trained this byte pair encoding. It's specialized to code, right? It's not like a pre-trained thing from so that's actually, it would be cool actually to see what are the byte pairs that show up in code. Are they different from the ones that show up in natural language? Like maybe underscores become really important, or something like that.
Yeah, basically all of the punctuation in the code becomes really important. Yeah, I think basically I looked inside the vocabularies. I think the first 10, 15 are kind of the combinations of basically of the punctuation. So semicolons, colons, so stuff like that.
Nice. And and actually that's an important detail of the byte pair encoding algorithm, right? It starts with the most important chunks. So you actually do get kind of an ordering of importance of how soon were these learned as to be a useful thing to encode. So it's cool that it's actually all punctuation. That's a neat result. I don't know if anybody's ever published on what the encodings look like for code. You mentioned that you switched over from TensorFlow Keras to PyTorch. So I was wondering, like a lot of our audience actually, works in both frameworks sometimes. It sort of like jumps between them. I often get questions from folks in our community, should I do this project in Keras? Should I do it in PyTorch? What's your recommendation? What do you think are the important things to help make that decision?
Just looking at the image of the of my model, right? I was having a lot of trouble fitting this kind of structure into basically into Keras. Basically, I had to. There is no way, at least I know, in Keras to encode or basically to have inputs of different sizes, right? So potentially you would have 3 Python samples, 10 Go samples, 15 Ruby samples, and as far as I could experiment, I couldn't come up with a way to make for Keras to make sense of that. So basically with Keras, I had to split up the models. Basically, there were six models, one for each language, basically one for each query and programming language pair, because that was the only way to have multiple languages, but that kind of loses the point where you have the same queries for all of the languages, and so you kind of lose on the when training, and that was kind of the first problem. The Keras model looked really weird, and it was kind of hard to implement it, at least for me. So and then the second problem was basically just the development problem with the Django. When locally developing Keras and Django, there were some weird threading issues I couldn't figure out because I don't exactly remember what it was, but basically when I ran a local Django server and it called the model, the TensorFlow model or the Keras model, it just segfolded or something like that, something really weird, which basically there was some threading issue that required me to run Django's in a single thread somewhere else or something like that. So that kind of culminated in me just looking into PyTorch and seeing that basically it was really simple to transfer all of the code, all of the code into PyTorch, and the model itself is actually really simple to implement in PyTorch. In Keras, it was actually pretty long. This is the model. Basically, these are all helper functions, and this is the forward. Basically, the forward function for training the model. Right. This is it. This is basically this does everything. And here are the encoding stuff. And I don't know. It just seemed simple. It was easy to deploy. The training was marginally faster with PyTorch, and because I didn't have to train 6 separate models, that also helped a lot with the development speed, and I was able to kind of iterate faster. And the model, of course, got better because queries were able to be shared between separate languages.
That's interesting. Yeah, I definitely have heard from folks that when it comes time to build, a complicated model in Keras, it's not as clear how to do that. I think there are folks in the TensorFlow community who do build these kinds of models, and they know the right way to do it. But I think what people's experience has been is that it's just a little bit harder to figure out how to do that than in PyTorch. So hopefully, I think they're both great frameworks, and I do work in both of them. So hopefully that gets surfaced, better. So that we have more flexibility in choosing which framework to use. Let's see. Oh, another question, a little bit broader. Why do you think the bag of words methods are so successful here? You mentioned, I think, a couple times that, people have tried 1D convolutions and recurrent networks of different kinds and not found great performance. So, do you have any intuition for why that should be the case, that these would work so poorly?
My first guess would be that there isn't enough samples. Like probably 6 million functions are not enough to train basically a recurrent model, or there just isn't a lot of information to get out. But basically, strictly from the challenge perspective, right? I think that a lot of the queries can be answered just by using a simple token search or something like that, which is basically what bag of words is. I think the queries itself, the challenge queries, are not that complicated, so they probably don't need any deeper understanding than just basically looking at tokens from the query, tokens from the code, and just kind of matching, kind of fuzzy matching them together, and you get a pretty good result. I think now with the updated results, the self-attention model was really close to the neural bag of words model. So I think that with some tweaking, the self-attention model, which I didn't look too much into, but I think it could be better than the neural bag of words model. I kind of had to tweak the original implementations so I could get it just right. But I think the main thing is just to get more samples. Basically, only 2 million functions are trainable, which have a doc string. So probably just more data, I guess.
Gotcha. And yeah, I know that to get those big transformer self-attention models working on natural language as opposed to code, people have found that, it's pre-training, right? It's being able to get a data set that's like, orders of magnitude larger than your supervised data set because there's no human in the loop. So if you were able to, code crawl all of the, all of GitHub, all of its public repositories, and just learn how to generate code, that might be helpful. They probably already did some pre-training in the self-attention one, but
probably, I guess. But yeah, my guess would be just more data. And with the neural bag of words model, there's a funny little issue where you don't, the model doesn't differentiate between, convert int to string or string to int. Basically, that's the same thing to the model, and it returns the same results. And a lot of the challenge queries are convert something to that, JSON to XML, and to get it working on that, or basically maybe just using a sequence model on the queries and then just a neural bag of words on the code might help to encode this kind of dependencies, right?
Gotcha. Yeah, that makes sense. Great. Well, I think that's about all the time that we have. So thank you so much for staying up late to be able to present your work to this community. And thanks for answering my questions. It's really cool work. Really, again, like very impressive. Oh, I did have one question that I wanted to make sure I didn't forget to ask you, which is, I think a lot of people in our community are on sort of like a similar track to you, where you're a full stack developer. You do, your day job is not machine learning and deep learning, and this is something that you've, like, a skill that you've added to your toolkit. So could you just comment on maybe the most important resources that you think are out there for following that journey? What was most important to you along the way, like the kind of, the advice that you would have liked to have gotten maybe when you were just getting started?
I guess from an engineer's perspective, right, just don't care about math too much at the start, right? Just kind of, I think it would be better, because I was worried that if I didn't understand everything behind that was happening, like the math, the back propagations, all of that stuff, that I wouldn't be able to come up with models on my own. So I would like, I think it would be great advice if someone could tell me back then that you can just start coding, start producing models, throw some data at it and see if it works. And if it doesn't, then you can go basically explore why it doesn't work. And then by basically using that, you can learn. But just kind of as a general resource, I think the PyTorch documentation is really good. The Keras documentation is really good. Basically, for beginners, Keras is great. The tutorials are great, and also the Kaggle competitions, or some of the not the competitions, but the stuff that is just like there for beginners to learn. There are a lot of great notebooks that basically implement either a neural network from scratch, or they're using Keras to basically train a simple model to predict something. I learned actually a lot from those notebooks because I could actually see the code and not just go through tutorials over and over again. I could just download I think the IPython notebook and kind of try on my own. Basically, just trying stuff on your own is the most important thing to get started. And yeah, just don't get stuck in the math at first. You can get stuck later, but just not at first. At least for non-machine learning practitioners, basically just people who are coming in from, I don't know, front end, back end, full stack developers.
Yeah, I think that makes sense. It's motivating, it's energizing when you make something, even if it's not perfect. If you make a cool tool for yourself, that's a nice way to get started rather than just slogging through textbooks.
Exactly. That would be my advice.
Yeah. Yeah. So it's, we sort of took, I think, two very different paths. I went in, did a PhD and had the chance to just get lost in math for a couple years while learning my way forward. But it's not a path I would recommend necessarily to anybody, or at least to everybody. So yeah, that's great advice, Rok.
Yeah, depends on the person. Yeah.
Mm-hmm. Yeah. Well, so thank you so much for joining us. I'll let you go now. So thanks to everybody for tuning in.